We leave mechanics behind and move to the second major topic of this course, thermal physics. It is not that we are not going to talk about force, work, and energy anymore in this topic. We will definitely come back to these quantities again, but in relation to physical processes where heat and change in temperature are involved. Heat itself is a form of energy. When we heat an object, a saucepan to make Maggi mee for instance, we observe the temperature of that object increases. The pan gets hotter, and so does the water inside it. This illustration shows that temperature is closely related to energy. In fact, you may think of temperature as some kind of measure to the amount of energy that an object possesses. When an object is being heated up, the object absorbs the heat. The heat energy is then embedded in the object and becomes the object's internal energy. An object with higher temperature carries more of this internal energy, and an object with lower temperature carries less of this energy. We will come back to this discussion on internal energy at later stage, but for now, let's concentrate on the temperature itself. Here in NUS, we become very concerned about temperature when the lecture theatre or the exam hall becomes unbearably cold. We asked our friend to check the thermometer, and he or she said 20 degrees. Wow, no wonder. In Singapore, we are accustomed to degrees Celsius as the unit of temperature, so when our friend shouted 20 degrees, we knew straight away that he or she meant 20 degrees Celsius. Not so in the US. If you ever go for an exchange program to a US university and similar conversation happens, your classmates would have shouted 68 degrees. Americans are accustomed to degree Fahrenheit, so what your classmate meant was 68 degrees Fahrenheit. 20 degrees Celsius is equal to 68 degrees Fahrenheit. The question is, what are these Celsius or Fahrenheit? How were these different temperature scales defined? Well, it turns out that these scales were defined rather randomly, or in Singlish, we say that they were suka-suka defined. In fact, it's pretty straightforward to come out with our own temperature scale. Seriously, though to make it adopted by others globally is a totally different matter. First, what you need is a beaker of ice blocks. We then stick a thermometer into the beaker glass. Now inside a thermometer is a liquid. It could be mercury or alcohol, but it must be a liquid which is sensitive to heat input and output, so that it easily expands when heated up and contracts when cooled down. Now we wait at room temperature. At the point where the ice blocks start melting, so we naturally call this point melting point, we take note the height of the liquid inside the thermometer and assign a number at that point. Now this was where Celsius took a different path from Fahrenheit. Celsius assigned 0 at this point, whereas Fahrenheit assigned 32. Hence, 0 Celsius became the melting point for ice, as we are all familiar with, while our American friends are familiar with 32 Fahrenheit as the melting point of ice. In the next step, we heat up the beaker, and we wait until the ice melts into water, and the water heats up and it starts boiling. At this point, which we naturally call boiling point, we take note the new height of the liquid column inside the thermometer, and assign a number at that point. We may assign any number as we wish, as long as it is bigger than the previous number at the melting point. Celsius assigned 100, thus in Singapore we say that water is boiling at 100 degrees Celsius. However, Fahrenheit assigned 212, and hence, our American friends say that water is boiling at 212 degrees Fahrenheit. The last step we need to do is to apply scales at uniform interval, so that we are able to find out the temperature in between the melting and boiling point by way of interpolation, and the temperature below the melting point and above the boiling point by way of extrapolation. In this regard, both Celsius and Fahrenheit agreed to apply unit interval in between the 2 points. Celsius had 100 units interval, whereas Fahrenheit had 190 unit intervals. Thus the ratio of Fahrenheit to Celsius is 190 to 100, or 9 to 5. This ratio gives a conversion equation between degree Celsius and degree Fahrenheit, and vice versa. By the same argument, we can derive the conversion equation between our own defined temperature to Fahrenheit or Celsius. As a matter of fact, there were actually many more temperature scales in the past. Some, such as Celsius and Fahrenheit, are more popular than the others, such as Rankine or Reaumur nowadays. But you can easily imagine that these differences show a lack of universal temperature scale, until Kelvin scale came into picture. The scale was named after Lord Kelvin, a British physicist cum engineer. Kelvin thus become an SI unit for temperature. It is also called absolute temperature, and it is related to Celsius scale by this equation. Hence, ice melt at 273.15 Kelvin, and water boils at 373.15 Kelvin. You may derive for yourself how Fahrenheit scale is related to Kelvin. Now, why did Kelvin scale become the absolute temperature? In what sense is it more superior than Celsius scale, or other scales for that matter? Where does this magic number 273.15 come from? If these are your questions, hold on to them for now. I will provide the answer in the next chapter when we discuss ideal gas. The last thing I would like to discuss in this lecture is what happens when two or more objects of different temperature comes into contact. For instance, what happens if our relatively colder hand accidentally touches a hot pan? Well, heat will be transferred from the pan to our hand, resulting in our hand burnt. In general, heat will be transferred from object of higher temperature to object of lower temperature. Heat will stop flowing when the two objects finally reach thermal equilibrium, meaning that both objects share the same temperature. The implication is, in reference to this picture, let's say object A is in thermal equilibrium with object C, and object B is in thermal equilibrium also with object C. Then object A will also be in thermal equilibrium with object C, even though they are not in contact with each other. Notice that all three objects might start with different temperature to begin with, but they will eventually end up with the same temperature. Physicists refer to this as the zeroth law of thermodynamics.